Welcome back to the stream. We are continuing work on our C interpreter today again. So last time we added implicit conversions, which is just something that it was really annoying before having to manually cast everything all the time. But now we get implicit conversions, and we've accumulated a bit of technical debt that I didn't have time to clean up in the stream. So for example, here we are in the code that handles implicit conversions for function arguments. We need to iterate over all the arguments and then insert a cast node when appropriate. And the issue here was that due to the way that this expression list is an intrinsically linked list, and this wasn't, I didn't find a straightforward way to like change a node within an intrinsically linked list, because we want to, so we have an existing node. So we have like an integer literal, which is part of this list, and we wanted to change that to add a cast node whose child is the integer literal. And I didn't find a way to do that in the stream, but I've implemented like a straightforward solution of grammar. So we just iterate over all the arguments, remove one at a time, do the conversion, which does the might add a parent node, and then add the new one back to a new list. And this works out nicely. And because it's intrinsically linked list, all this list shuffling doesn't do any dynamic memory allocation. So we properly handle conversions. And then the other thing that we're having the other issue was with what I'm looking for. The other, all right, and then we had the parsing issue. So the issue is that like a cast expression like so is not distinguishable from like a plain old parenthesized expression just by looking at the parents, and this caused like parsing issues. And I fixed that by when we pass a primary expression and we have an open paren, we can then afterward distinguish between a cast or plain old parenthesis. So we have a cast if we have a type name, otherwise it's a plain one. And this doesn't, strictly speaking, doesn't have the correct precedence as specified in the grammar, but it just works out in this case. So it's a bit of a hack, but it works. Okay, so the plan for this stream is to add more integer types. So hang on a second. Okay. Okay. So to add smaller integer types, and I've already alluded to that a couple streams ago. So the issue is that we're having our int means 64-bit. And then we have short int, but we want to have both 16 and 32-bit integers. So the idea is that short means 32-bit, and then we add short as an extension to mean 16-bit integer. Okay, so let's start with short. We need to add a new integer type. So we've got signed in 32 and unsigned in 32. And then we are also adding a new type specifier, the modifier short. And then just fill in the enums. So here, when we make unsigned, and we're having un32, we can in fact unify that one like so. So if we have an unsigned type, we do nothing. And if we have a signed in 32, this turns into unsigned int 32. They have integer rank 32. So 32, 32, 32. And when we print them, 32, 32, 32 and 32. Right, this is the specifier. And there's also the specifier. Okay. And then for the specifier, so we want to pass a new specifier. So let's add it to the list of type specifiers. So we've got short, which is the type specifier short. That is straightforward. And then, so when we're having a specifier that is short, like this is another modifier, type specifier short. Okay, I've having issues with the Wi-Fi. I hope it's okay. So if we have a type specifier short, we need to keep track of how many shorts we have. So we allow at most 2. So short count 0. Okay. So when we have a short, we increment the short. We have an error if we already have to. Then we log an error for invalid type specifier. Otherwise we increment it. And then the base type, if the base type is void, or rather more precisely if the base type isn't int. Now, if it is void. So if the base type is void, then we also log an error. And yeah, otherwise we increment the short count. Okay. Then we don't need to handle those. In fact, let me just add default. They are not possible base types. I'm still getting not enough video. I'm just quickly restarting. Okay. So then we need to adjust. So if we're having assigned in 64, we need to look at the short count to figure out the size. If the short count is 0, then we return assigned in 64. Otherwise, we return assigned in 32. And like so, if we are in the unsigned case and the short count is 0, we return u in 64. Otherwise, we return a u in 32. And that should be enough to like create the proper est. So now we're creating a variable decal I, which is assigned in 32. We're apparently not handling implicit conversions in the initializer, so that's a different bug. And we're also not handling it in the backend. So we're still allocating 8 bytes, even though it's a 32-bit integer. So just so we get an implicit conversions, let me change here to use assignment and then fix the implicit conversions later. So we should be... Oh, interesting. Okay, so we need to adjust the conversion code to allow implicit conversions between the integer types. This is here. Right, it's arithmetic. Here we go. So we haven't adjusted those. So I believe it would be a good idea to use a switch here, so we get a warning. So if built-in is null, then we return false. Otherwise, we switch over the built-in type kind. And if it's assigned integer, then we return true. Otherwise, we return false. My Wi-Fi apparently doesn't like me today. And then similar here for the unsigned. Okay, So that's that. And now now we're getting the correct cast. So we're casting the signed in 64 to a signed 32 for the assignment. And then we're getting an assertion failure in CodeGen. Of course, no. Okay, interesting. So we need to handle this new kind of conversion. So we need to handle a conversion from a smaller integer to a bigger integer. Okay, and actually, so here's the thing. When we do something like short AB, I equals A plus B, this never actually does an addition between shorts. This always adds integers. Because in C and also in C++, everything that is smaller than int gets promoted to an int before you do anything with it. So whenever we have intermediate values, we're dealing with ints, not with shorts. And the same is true for the low VM. So it's the stack-based VM, so we're pushing values onto the stack, but stack values are always 64 bits. So we will never dealing with a value that isn't a stack value, and that isn't 64-bit. So when we do like a conversion between like a 64-bit integer to a 32-bit integer, in the expression context, we don't need to do any conversion at all because everything is there, is always 64-bit anyway. Only when we actually store the value into memory is the type important. Will it then be truncated? So when we are asked to do a conversion between a 64-bit and a 32-bit integer, we don't actually need to do anything. So if this means that if we are asked to do a conversion and the target is unsigned, then we potentially need to do a signed unsigned conversion with overflow checking. Else, so we only need to convert. So else we add a precondition that it is already signed. If it is also signed, then we don't need to do any conversion. The type itself, all stack values are 64-bit anyway, so we will never need to cast between them. And then similar here for the other way, so we need to do a conversion from signed to unsigned, and otherwise we don't need to do anything. Okay, so now it compiles again. We're handling the conversion, but we are not actually handling the variable correctly. So we need to adjust the storage size because we're having 8 bits, but we're only having fewer than that. Okay, and the way this is done is we are having, like, for example, the code for a variable decker. Where is it? Right here. This builds a local with a given layout. And we're currently hardcoding the layer to the default 64-bit value, and here's a to-do already that reminds us that this is incorrect. So we need to write a function that maps a type to a layout, or rather a low type. Okay, so let's write that function. So I guess I can do it. Let's do it right here. So we want to map return allow as a type. I don't know whether they actually passed by pointer or not. Might be. Let's see. CodeGen type from a cloud type. Okay. So we can do that by doing a visit over all possible nodes. The first kind is a cloud built-in type. And then we are switching over the type kind. If it's void, we are unreachable, not needed in loaf. So void types don't exist in the loaf level, so we don't need to worry about them. 32-bit integer, so similar to LLVM, loaf doesn't do a distinction between signed and unsigned at the type level because they're having the same size. The distinction is only made on the operation. So for both of those, we're returning the same type, which is loaf lib int signed 32. No. Oh, we actually do make a distinction. Never mind. Oh, I know, right. So we make a distinction due to overflow checking. So U32. Wait, I have an S32, but I don't have an. Yeah, U32. I don't know why. Autocomplete didn't like that. Oh, because it's duplicate. That's okay. And then like that, signed 64 and U64. Okay, and then the other case. So if you're having a function type, not the type of a variable. So we don't need to worry about that one either. Okay, and then we need to just return a value to make the type checker happy. So now type value, the generic default type is fine. Okay. Now this returns the correct type. And now essentially, whenever we're using loaf as on type value, we now need the correct type. So go code gen type. I believe type. Wait. What is parameter as a vector of parameter decals? Oh, it's a. I need the double depermanency. Okay, I thought we code gen the type, and like here, var type, decal type, and then code gen type, code gen type, local var, var decal. We are using it multiple times, so let's do it right here. Var decal type, 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 and then here again. So here, pass the correct type, and store the value into the address. The value. What's the address? So this one also needs to set a type. Type, code gen type, var decal type. And here for the param decal. So we're getting the type, we're converting it, we're setting it, and then we can access it here. And then layout off. So here we are having the same deal. Code gen type, decal type, layout, and like here. So we get the type, and then we also get its layout. And again here. Layout. Type. Okay, and what all this is now doing is that we are creating still a local allocation for 8 bytes. And okay. That is not what I expected to do. Oh, I know what's going on. So a couple things changed. This doesn't seem correct. Okay, so we are allocating 8 bytes. This is because I believe we're not supporting any allocation smaller than 8 bytes. So we'll always allocate 8 bytes. But now when we actually access it, we're getting its address. I don't know what this byte prints 8192 here. I believe this is a bug in the load, like in the bytecode dumper, because it executes fine. So we're getting the address, we're dereferencing it, and we request need 4 bytes. And then we're calling store for signed 32. And when we had like a plain int, this looked a bit different. So for plain int, instead of a local allocation, we're directly doing like a local storage, which is a more efficient way, because this is a view. So what's going on here is instead of calling like a built-in function to do the store, we're calling an intrinsic that is designed to store a value of 8 bytes into a local variable. And that is more efficient, because what this code is doing is it checks that the pointer is valid, which has overhead. And here we are hard coding like the address of a local variable in the instruction, so we don't need to do any checking because we know it's always valid. But this is only available for 8 bytes. And then we are also not creating a local allocation, but local storage, which is just memory that isn't tracked by the underlying system. So this is a more efficient optimization, but it essentially does the same thing as here, just streamlined. So what this now means is that we can correctly store signed 32. Now the first thing that's going on is what happens if we are having a value that's too big. Nothing happens. What happens if we print it? Print I. Okay, so this, I'm surprised, like this round trips so nicely. Why does it round trip? I mean, I've expected to like truncate it, but it didn't. But that's interesting. Like what does it actually, like it loads? Oh, it probably does. Yeah, I believe I know what's going on here. So when we do the type signed 32, if we go to the definition, it has a load instruction and a store instruction, and the load one does a sign extension. So what we are storing here is so we're storing truncate it to 32 bits, which is -1 for signed value. And then when we load it, load the sign extension to like essentially to like the full 8 bits again, which is also -1 as a 64-bit number. So that's why it worked. So to actually like we need to like put the 0 here, and now it will no longer do sign extension when it loads. Right. So now we are only getting a couple of the values back, because the store only stores like those bits into the value, and then when we load it, it does not do sign extension. So okay. Now of course the C standard actually, like this is signed overflow, which is undefined behavior. So we should actually check handle that. And like the ideal way, like the conversion would check that this is in range. So let's actually, yeah. So ideally, when we do the conversion, cast expression. So at this point, we should do bounds checking to ensure that we are having a 32-bit value that fits in 32-bit. But that is a bit slow if we do that like for every operation, because we're like constantly converting between them. So instead, we can do a more efficient one and do a check only before we store. I believe. And that's also no. Okay, let's do it here. So let's start by signed. Okay, so let's check for overflow. Just check for overflow. But only if the type is smaller, if you're converting to a smaller one. So the target rank zero integer rank of the type of the expression and the source rank, which is this one. Okay. If the target rank is smaller than the source rank, then we need to check for overflow. This is done by switching over the target rank, which can be, in this case, like so. Forgot to add size. Okay, I don't. It's not. I don't like it. But this second. So if the target rank is 64, we don't actually need to do anything. Do not have values bigger than 64. Okay. Otherwise, if it's 32, we're calling a built-in. Now Adam built-in lib-int F32 overflow, this one, which checks whether we have overflow. So this built-in checks whether the value is overflown and returns true or false. So if it's true, then we want to panic. So let's add yeah, actually, let's just for consistent also do, because there is a 64 overflow which always returns false. And then at this point we can do like overflow block. And then build input vstack size of the current one. Builder. So we create a new block and then we do a conditional branch. So if overflow is true, we go to overflow block. Otherwise, we go to continue block, which we also need to declare. Go to continue block. If we start building the overflow block, then we do a panic. And we also need to give it a message that an integer overflow occurred. Which requires like that we add a global, okay. And so let's just give it no message for now. to do message, and then we continue building with the continue block. Okay. So now branch targets input count, not count blocks output count. What? Oh, right. Because we moved the condition. We're having one fewer on the stack. Okay. So now we're getting a pending for overflow, and ideally we would have a better message here than invalid message pointer. Okay. So this is a very cool constant folding that happened here. Because like it's completely elided all the branch because it knows statically that it overflowed, which is quite cool. But anyways, so this is a bit of an overhead to do like the conditional panic here. I should probably like do like a panic if instruction so we don't need to generate the basic blocks, or even better handle it here somehow. But anyways, that's that. Note that again, signed overflow. I'm sorry, or overflow checking. Because if we're having unsigned values, overflow is fine, it just wraps around, so we don't need to worry about it. Okay. So that's that. Let's commit. But we are still not quite done. So what we are not handling correctly is when we do like addition. So AB 11 42. If we do something like this, what we're doing here is we're doing addition on signed ins 32. And this is fine, this works out. But what we're actually doing, as I said, is all intermediate operations are done on 64-bit. So we're also doing like a 64-bit addition instead of a 32-1. And this is fine, this is what the standard says anyway, because of integer promotion. So if we go to the standard, and this isn't a coincidence that low and the standard works the same way. CPUs also work similarly. So for example, for addition, usual arithmetic conversions, we already do that. But we're not doing them completely. We are forgetting one. We haven't implemented one thing. Conversions. So the usual arithmetic conversions. Integer promotions are performed on both the points. So what we need to do is we promote both of them to int before we do anything here in the usual arithmetic conversions. So when we do to CodeGen, not CodeGen, compiler, usual arithmetic conversions, we need to do integer promotion. So ls do integer promotion. On both of those. And then performs integer promotion. See now expression, do integer promotion, compiler state. We don't need the location because actually, we need one for the new cast operation. Location, expression, expression. So, if we don't have an integer, then we don't need to do integer promotion. Otherwise, we get which kind of integer it is. So clof, built-in type, expression type kind, and switch over kind. This is unreachable, not an integer. Let's use like a target type here. And then the target type is null pointer. Okay, so if we're having assigned in 32, so what does this standard say about integer promotion? So we define a rank. Where does it say? Where does it specify integer promotion? If the values are converted. Yeah, right. The value from a bit field, if the original type is not, here we are. And if an int can represent all values of the original type, the value is converted to an int. Otherwise, it is converted to an unsigned int. These are called integer promotions. All other types are unchained by integer promotions. So this essentially means if we have an assigned in 32, we can represent it by an assigned in 64. So we convert it to assigned in 64. State as types. State as types lookup or create. Steal of built-in type. Steal of built-in type. Signed in 64. Similar for un32. This can also be represented by assigned in 64. And this is a bit annoying in the language because we're having, even though we're having an unsigned type, we're converting it to a signed type. So a short, unsigned short gets promoted to int because an int can represent all values of it. And those ones are left unchanged. So we return the type of the expression itself. So if we're now having a target type that is not this, so if we're having a target type that is not the same as the type of our expression, or if it is the same, then we didn't do anything. Otherwise, we create a new cast expression at the location to the target type of our expression. So we've promoted. And here there is a convenience method, create built-in type. Okay, so that's integer promotion. We also need the state and the location. The state and the location. And now we are doing, even though we're having two shorts, we're promoting them both to int and then doing arithmetic on an int and truncating the result back to a short before we do the assignment. And this is like really weird behavior, but it is what the standard specifies, and it's also what is naively implemented by Loaf anyway, because we are loading assigned in 32, which pushes this on the stack as a 64-bit value. Then we're loading another one, which pushes it on the stack as a 64-bit value. Where exactly am I? All right, here. So this loads the second one. Then we're doing the addition, which results in a 64-bit value. And then we're storing it back into assigned 32. So we're doing an overflow check, which might panic. And then we're storing it back into assigned 32. Okay, so that is integer promotion. Okay, so let's commit that. Implement integer promotion. So then there is a bug where we're not handling initialization correctly. Right, so we're initializing it with assigned 64 and should have casted it, but we're not doing that. So let's find the place where we're doing a variable decl variable declaration. So somewhere in here, we are creating a new variable without an initializer. Okay, so where do we add the initializer? Right here, do we add an initializer, and we need to do an assignment conversion. Init do assignment conversion state state as location of our of our variable. Let's use that at the location. And the target type is the type of the declaration, and the value is the initializer of the initializer. So I can't call this init converted init, and then we set the initializer to the converted init. Helps if I can spell. So now we are doing inserting a cast in here correctly, which means that we would also do an overflow check if we didn't have a constant value, and which was then constant folded away, right? Let me see. Yeah, so we'll adjust, this is the initializer, but it has been constant folded. So the overflow check has been constant folded away. So we are pushing the value. It generates like a weird block instruction here, which is again, like I need to look, there are a couple bugs in the printing, like I don't know why it prints 8192 for the local address. Absolutely no idea. But okay, so this was a bug fix. We're handling conversion at the initializer. Implement conversions for variable initializer. And then we're having 32-bit. Now it's quite straightforward to add 16-bit. So 16, and the idea was first we fix all the innovation values. So make unsigned. If we're having u in 16, that's already taken care of. If we're having assigned int 16, we get u in 16. So assigned 16, unsigned 16, unsigned 16, and here we have assigned 16. The rank here is 16. We are printing it using 16s. And 16 during codegen. We are having the corresponding 16 types. During integer promotion, we also promote them to 64-bit. And then we need to add them in the cast expression, right here where we need to do the overflow checking. Overflow checking for assigned 16-bit. And while we're at it, let's just also add the 8 one. So now we've got all overflow checking implemented. The library doesn't provide anymore. So that's that. So now we are compiling. And we need to just tweak the compiler a bit. So when we are having the type specifier short, so the idea was that 16-bit integer is a short, which is like a fun syntax extension. So if the short count is 1, then we're creating a signed int 32, and if the short count is 2, we're creating a signed int 16. Else, yeah, let's say if the user specified more than that, we issue an error, and then we still give you a 16. 1, and then else a 16. And now we can add our short, which is like a fun syntax. I mean, long is already a thing, so why not have short? And now we're doing like 16-bit stores and 16-bit loads and 16-bit overflows and so on. So that just works. And just for completeness, throw in an unsigned and throw in an int in here, just so we can see that the parser handles all the fun ways you can declare variables in C. But it did. Wait. This is now treated as like a 32-bit value again. So we did some sort of... Okay, so somewhere I had made a copy-paste error. U32. Wait, why are you? Did I make a copy-paste error here in the library? No? Interesting. So we're having an unsigned short. So this is all correct. Like, we are dealing with un16s that we convert, like we do addition unsigned one and so on. So that's fine. But then we're creating a u32 stores. And we are only dereferencing 1 byte. What? We're supposed to... So something's really messed up here. Right, if we didn't have the unsigned one, like we're dealing signed in 16, so that's fine. And then we also like dereference 2 bytes and 16 bits. But something breaks when we go to unsigned. And during code gen, so u32 is only mentioned here. And the un16 like this is also correct. Okay, I have to look at the debugger. So where do we do what's the best way to put it? So we're doing like so this code isn't triggered at all, right? So that's that. So when we do a load of a variable, so identifier expression, right here. So we are loading a vertical, and the name, we can't really get the name. C-string. How do we get like the name of it? So we've got like the state somewhere stored in the context, context.state.ast or something. Context.ast symbols, like so. No. Okay. It doesn't matter because everything has. So where are we? Identifier expression. So we're in here. So then we got in the type. What was the type? The name is u16. So that is correct. And then we are pushing a local address, and then we're loading a field. So now this appends to do constant folding. It fails to do constant folding. So what is the layout of the type? Okay, so the layout is wrong. That's the first issue. Why is the layout wrong? I mean, it's a constant, so it's probably set wrong. Okay, so the layout is wrong. We're pushing a field index, and then we are calling the type for the load function. Okay, so that all seems correct, but the layout is wrong. So now we know why this is calling with the wrong one. The layout is wrong. So why is the layout wrong? U16. What does this one here mean? I know there's number of fields. Right. So we've got a copy paste error out here. Layout of U16. Okay. So now we're getting the correct layout. We're still calling the wrong store function. Why are we calling the wrong store? Oh, right. And then because this one. Okay. Too many numbers in here. So we were calling the correct one, but this one was wrong, so they shared the same name, and then when it printed one, it found this one first. Okay, so the actual bug was with the UN32. Okay. So this is something that I need to commit to Loaf. But other than that, we implemented 16 bits. Add short as an extension for 16-bit integers. Okay, and while we add it, let's also add signed and unsigned char. So one last time, we're adding new integer types. Signed int, unsigned int. Then we are having the same error messages again. You want 8. This one here should unit 8. Oh, right. That's why it didn't. Okay. Unit 8. So signed 8. Unit 8. Unit 8. And signed 8. They have the integer rank 8. They're printed accordingly. 8. And we cojoin them as 8-bit integers. And when we do integer promotion, we promote them to 64-bit. Okay. So now we're still compiling. Oh, we need to fix the seg fault on the test later. So we're compiling, we add them the specifiers. So we've got a new base types, underlying type specifier, which is called char. So when we go on the compiler, what we're doing here in type specifier, but here we have a new type specifier char. And when we then pass we will get an error right here. Okay. So we're passing a bunch of type specifiers. And when we have the type specifier char, we set the base type to char, which is signed. Actually, we don't actually have char as a base type. So the thing is that we've got like int, which is the same as signed int, which is not the same as unsigned int. However, we have char, which is not the same as signed char, which is not the same as unsigned char. Because C. So those are 3 distinct types. And when we're just having a plain char, we need to update the base type to plain char. But I don't want to add a plain char type right now. So to do set base type to char, not signed char. I don't want to add one. We will add that when we add string literals and so on. Then we will add char. For now, we just want the integer. So we just set it to signed char. And so when the base specifier right here is signed char, or other, right, ideally this would be the base one. We do a similar logic like so. If is signed value are true, then we return, again, I can simplify this code here to just say create, 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 and create. And then similar logic like here, if it is signed, then return state as create 0 built-in type signed 8, else we assume it's unsigned and return a u and 8. Okay, and now this should be enough to just get signed char a to have like two plain 8-bit integers. So again, we're doing 64-bit, casting them to signed. We're doing addition on the 64-bit values due to integer promotion. We need to allocate a bunch of memory because we don't support allocations smaller than 8 bytes, so we're wasting a bit, but that's fine. And then we are doing 8-bit loads and stores and 8-bit overflows checks. So that works. And then when we do char unsigned, we're having like a bunch of u and 8s, but we're still doing addition on signed in 64 because integer promotion rules. And then we're also not doing any overflow checking because this would wrap around. Okay, and like this is now currently treated as a signed char, which is incorrect because char is not the same as signed char. So we should really handle this as a different type, which we will do later on. Okay, so that's the last integer type there for now. So like the there's also like long and long, which would be like makes sense to map to like 128-bit integers, but Lauf doesn't support them at the moment. So add 8-bit integers. Okay. So I noticed while looking at the modifying the code right here, where we do like handle this logic. For example, when we have add a short modifier, we create an error if we're having an invalid base type. So if we have something like void short a, which like so, this short would trigger this error right here because the base type is void and not int. However, if we're having short void, we would not trigger an error because when we pass the short, the base type isn't set yet. So actually the correct place to handle the invalid base type is not when we do the modifiers, but when we actually like at the very end, when we look at the base type. So for example, for void, if is signed.has value, so if we have assigned modifiers, then we issue an error. And like here, if we're having a short count, so we cannot have a short char. So we log an error. And here we're allowing both signed and short. Okay, great. So just to demonstrate that this works, if we're now having a short char, we get the very convenient error message, which tells us exactly what's going on in relative combination of type specifiers. Not the best, but I can't be bothered to, like, it's a lot of work to generate good error messages. We need to keep track of a bunch of things, and I don't think it's too interesting. Okay. Generate more error messages for invalid type specifiers. And finally, the tests currently have a segmentation fault. So let's figure out what's going on here. tests integration if.c. We indeed have a segmentation fault. Because we're having a var decal. Right. This isn't a var decal, this is a perm decal. Okay, that was a very easy fix. It's so annoying that when we do like an if with initializer, the variable that we're declaring here is also in scope here, even though it's not, right? I make this bug all the time, which is why I was so quick to fix it. So annoying. I also should maybe like copy paste this, but that's a different thing. Okay, let's do fancy. So we added this somewhere when we added short. So let's do a fix up on the commit where we added short integers. Yeah, that should be the one. Okay, so now we're fixing this one while we added, let's how did the other one add? Signed, unsigned char, just to get the error message a bit more consistent. Okay, so with that, we've added now a bunch of integer types and handled all the implicit conversions, which is like a pretty good place. We've got like a pretty basic subset of C right now. So next week, I plan on tackling L values properly. There are a couple of to-dos, like here when we do assignments. So we're currently not checking, like we were able to do like 42 equals 11, which is code that we're not rejecting. It will probably just crash when we go to CodeGen. And then there are a bunch of other things, like for example, we don't have ++i. And those sort of things. So I'll do that next week. And then I will move on to pointers, which can be a lot of fun to add, especially because Loaf is a fully memory safe interpreter. Like it checks all pointers for validity. So like we will never get a segmentation fault in our interpreter C. But that's the plan. Thanks for everybody who stopped by. Hope you enjoyed the stream, and until then.